Thanks everyone for being here. We're so glad you could join us. This is a joint meeting between the physical oceanography team and the ecosystem team. And this Arctic Systems Interaction webinar series aims to explore the characteristics, mechanisms, primary drivers, and predictability of different types of Arctic extremes. Through this series, we will be examining the variability and trends, model representation, prediction, the impacts of various Arctic extremes, as well as their interconnected nature amongst Arctic systems. And this session today will focus on the effects of a marine heat wave on the ecosystem in the Gulf of Alaska and the Pacific Arctic. We have two fantastic speakers for you today. First, we have Mike Litzow. He's the program manager at the Kodiak Laboratory Director of NOAA. And we have Cody Szuwalski. He's a research biologist at the Alaska Fishery Science Center, also part of NOAA. So our first speaker today will be Mike. I'd like to turn it over to you, Mike. Thank you for being here.
Okay, thank you, Jackie. I'll just get my slides up and get that out of my way. Okay. Well, thanks for the invitation. And I'll start off by just acknowledging my co-authors on the work I'll be presenting today. This is very collaborative work that I'm going to be talking through. And I think the other important thing to say about the group of people who did this work or are doing this work is that we're all fisheries biologists. So we're really coming at the issue of marine heat waves from a sort of an end user perspective. And in particular, having trouble advancing. Let's try this. There we go. In particular, our interest in marine heat waves has really been spurred by this run of extreme events that we've been living through in Alaska since 2014. We've seen a number of historically unprecedented population level and ecosystem level consequences of those heat waves. Cody's going to be talking about the top example that I've got on this slide here. There's this other salient example with this unprecedented collapse of a ecologically important seabird population. And there's any other number of consequences that we've seen playing out for fisheries in the Gulf of Alaska and the Bering Sea. So really the central question that we are trying to get at in the work I'm going to be talking about today is how can we improve our understanding of the nature of changing risk for marine heat waves and extreme events in the Gulf of Alaska and the Bering Sea. So I'm going to try to combine two different studies in my talk today. In the first study, what we were aiming to do was to calculate how the anthropogenic influence on Gulf of Alaska and Bering Sea, Eastern Bering Sea, sea surface temperature has changed over time. And that study was published a couple of years ago in Environmental Research Letters. And then in the second study I'm going to be talking about, we look at non-anthropogenic risk factors for extreme events, particularly internal climate variability and how that might be playing out into more recent risk for extreme warming events in Alaska. So I said at the outset that we really come at this work from an end user perspective, a fisheries perspective, and that's particularly true with this first study, where the work really came out of a series of conversations with Gulf of Alaska salmon fishermen, fisheries stakeholders, about the sorts of information that people might need to make adaptation decisions effectively in a rapidly changing ecosystem. It turns out there's this whole really interesting literature on what kind of information is useful for effective adaptation decision-making. And I won't go into that at all today, but I'll just say that that literature points to the need to recognize, attribute, and anticipate change to make effective decision-making, adaptation decision-making. So this study turned into a peer-reviewed paper, but it was also one of the really important outcomes of this work was a series of outreach presentations that we did in Gulf of Alaska fishing communities. Okay, so as we're starting to talk with stakeholders about information that's needed for effective adaptation decision-making, this is the sort of the state of the system when we were starting this study. So we've got annual mean sea surface temperature from ERSST for the Eastern Bering Sea on the left, Gulf of Alaska on the right. And beginning in 2014, we saw that run of really extreme, unprecedented values in the two systems, and in the text boxes there, I've highlighted a number of the fisheries disruptions that occurred with those marine heat wave events. There were some range expansions, some population booms, but then also a number of really consequential, economically and socially consequential fisheries collapses that went along with these marine heat waves, or resulted from those marine heat waves. And so the first question we want to ask is one that centers on that attribution part of adaptation decision making, and just simply, were these extreme temperatures caused by humans, or was this something that we should have expected in the normal run of events in these systems? So to answer that question, we're going to use the most established attribution statistic in the climate literature. That's the fraction of attributable risk. That's just 1 minus the pre-industrial probability of a given event divided by the current probability of a given event. So fraction of attributable risk of 0 means that a given event is equally likely with or without human influence. 0.5 means that an event is twice as likely with human influence. And then if you get up to a FAR of 1, that means that you're at this fixed state where you're seeing anomalies that are only possible with human influence in the system. And you need climate models to estimate the factual current and counterfactual pre-industrial likelihood of a given event occurring. So we use an ensemble of 23 different CMIP6 models to make those probability estimates. And this was a really interesting part of the work for me, because I had never really worked much with climate models. It was remarkable to see the range in bias, even over areas as large as the North Pacific, for something that seems as simple as annual sea surface temperature variability, or annual sea surface temperature values. So anyway, to use this range of model characterizations of the system effectively, we used a model weighting approach based on skill and independence relative to observations. And then we also weighted for differences in climate sensitivity and predicted warming rate in the system. And this is all just to say that we want to get away from model democracy. This is not a situation where we want to just average all models uncritically. And then we took those weights that we generated, plugged them into a Bayesian regression framework, and produced our FAR estimates over time, our time series of fraction of attributable risk estimates. And those estimates are what you see here. So we tracked, or we produced attribution statistics for 2 temporal scales of sea surface temperature variability, an annual value in yellow, and then also a 3-year running mean in blue. And that 3-year running mean is important for a lot of fisheries outcomes, where you see much more sensitivity in the ecology to persistent perturbations over, say, a 3-year time span. So that's why we're interested in that statistic. The take home here is that, first of all, the North Pacific has been fixed at an anthropogenically, has been fixed at a state of temperatures that we expect were only possible with anthropogenic forcing for decades now. So the question of attribution at the basin scale is already moot. And then you see all the other ecosystems, particularly for the 3-year running mean, reaching these FAR values of 1, or very, very, very close to 1, indicating temperatures that were only possible with with anthropogenic radiative forcing. We do see FAR values exceeding 0.5, that value of twice as likely with human influence as without human influence. For the 3-year running means, going all the way back to the 1980s for the Bering Sea, and the 1990s for the Gulf of Alaska. So there's some indication of Arctic amplification in those results. And then something that was really interesting to me when we did this analysis originally is that we see these spikes of high attributable risk early in the time series in a number of ecosystems. And that was always sort of a little mysterious to me, a little difficult to understand. And I'll just point out this Clavins et al. Paper that came out in Nature last year that points to anthropogenic forcing of the PDO going all the way back to the 1950s. And I'm really interested in understanding how these results on the right might play in with the mechanisms that those authors are invoking. So with that first sort of set of information that we generated to provide to stakeholders, we can say that these warming events for the Eastern Bering Sea were almost certainly human caused and very likely to be human caused in the Gulf of Alaska. So another really important part of the attribution decision-making landscape is that people, humans across all sorts of different societies, traditionally use lived experience to evaluate risk going forward. And in a system that's being monotonically driven in a particular direction, that historical perspective on risk creates vulnerability for resource users. So we also want to generate information for stakeholders about how risk has changed over timescales that are relevant to individual fishermen's career in this fishery. And so to start that part of the project, we just developed this very simple statistical model where we looked at log catch anomalies for Gulf of Alaska sockeye salmon commercial catches on the y-axis versus a normalized temperature at ocean entry on the x-axis. And you can see above normalized values of 2 for ocean temperature, we get this set of much worse outcomes in log space for fisheries catches. So we'll just identify that value of 2 as a critical value for this, where you start to get very negative consequences for this fishery. And then we just used that same ensemble of 23 CMIP6 models to estimate the probability density of exceeding that critical ocean temperature value for this fishery at different states of warming for the North Pacific Ocean. So we used a baseline period of 1850 to 1949 because we were interested in capturing quite a long reference baseline period to capture different states of internal variability in the system. And then we're looking at the probability density of exceeding this critical value in the dashed vertical line at up to 0.5 degree of warming in the North Pacific, between 0.5 degree and 1 degree, 1 degree and 1.5 degrees, and then 1.5 degrees and 2 degrees of warming. And so to my mind, this is a simple, our goal was to create a simple but robust way to evaluate changing risk for a particular set of stakeholders. And in particular, the message that we were trying to convey is that lived experience for someone who's fishing now, who might have been fishing for the last 10 years, indicates that those critically warm sea surface temperature occurrences should be a minimum of expected outcomes. But if you shift forward from, say, 0.5 degree to 1 degree of warming to the current state that we're in now, between 1 degree and 1.5 degrees, suddenly that critical value is at the median of expected values. And then once we exceed 1.5 degrees of warming, the median expected temperature is actually above that critical value, which we've seen poor performance for the fishery previously. So just to understand what we're trying to do here, we're really trying to produce a simple but robust set of information for stakeholders to make adaptation decisions at timescales that are relevant to a small family business that's involved in this fishery. There are lots of caveats in this kind of approach. It's much simpler than the sort of ecosystem model or multi-population population dynamics modeling approach that is often used. And so we're very aware of the potential shortcomings of that simplicity. But then there's also, I think, benefits for avoiding complexity in terms of giving people actionable adaptation information. And then the final point we made in this study for stakeholder information is just that the rate at which we're going to reach those different ranges of North Pacific warming depends on mitigation efforts. onwards. So here we're just looking at those different thresholds of North Pacific warming that we use to frame out expected outcomes for the sockeye salmon fishery. We're comparing observations in yellow with two different social and socio, I forget the SSP acronym right now, but two different emissions pathways going forward. So you can see there's good agreement between observations and the two pathways for 0.5 degree and 1 degree of warming that we've already exceeded. And then you start to get divergence in the expected outcomes, the expected trajectories of warming relative to that pre-1950 baseline period. Okay, so that was study one. I'm just going to pay attention to my time here. Study two, we're sort of stepping back from anthropogenic warming as the leading risk factor for marine heat waves in Alaska. And we want to focus on internal variability that might also contribute to that risk. And this study really came out of this observation that's been bubbling around in the fisheries and marine ecology literature in Alaska for a number of years, which is that it seems that we used to have a lot of interannual variability in temperature in the Gulf and the Bering Sea, but in more recent decades, we've gone through these stanzas of either cold or warm runs of temperature anomalies. And stanzas, in the physical literature are just another term for red noise. So that concept of red noise will probably be familiar to most people in the audience. Red noise is a situation where you've got random variability and the state of the system at any time step is correlated with the state of the system at neighboring time steps, and that differs from white noise where you've got uncorrelated random variability. So if you have the same trend, a white noise system has very limited departure from the trend, but then a red noise system, departures from the trend tend to persist, and you get these persistent anomalies just through the autocorrelation in the time series. And so for this study, we want to address three questions. First of all, is temperature variability in the Gulf and the Bering Sea actually reddening? Then number two, can we explain why that is? And then number three, what are the implications for the risk for persistent marine heat waves in these two ecosystems? And the first question is pretty easy to answer. Yes, the answer is yes. Sea surface temperature variability in the Gulf of Alaska and Eastern Bering Sea has become redshifted, has become more autocorrelated in recent decades. And we just addressed that question with first order autocorrelation coefficients estimated on 15-year rolling windows. And we get these peak values recently in the Gulf of Alaska. And in the Bering Sea, we're getting autocorrelation up above 0.8, at which point you can really expect persistent departures from the mean just through random variability. I'm not going to go into it because of considerations of brevity right now, but we did look into the explanation that redshifted variability might be an expression of climate change in the system, but we don't see similar trends of redshifted variability in other boreal ecosystems, and we don't see an expectation of increased redshifted variability with anthropogenic forcing in the CMIC6 ensemble. So we're going to rule out climate change, at least as a first order explanation for that redshifted variability. And then what we ended up focusing on to try to explain why these two ecosystems have become more redshifted is non-stationary interannual variability in the Aleutian low. And this is something that I've worked on with colleagues in a variety of papers where we see real ecosystem consequences in the Gulf of Alaska based on whether interannual variability in the Aleutian low is very large or more muted. And to measure the interannual variability of the Aleutian low, we just looked at standard deviation of sea level pressure anomalies in this square over the same 15-year rolling windows. And those are the dashed lines in the top panel and the bottom panel. Those are the same Aleutian low time series. And then the colored lines here are the 15-year rolling window autocorrelation time series for sea surface temperature. And sure enough, statistically, those two line up. Periods of low variability in the Aleutian low are more white noise dominated for sea surface temperature, high Aleutian low variability is associated with more redshifted variability in sea surface temperature. So there's a statistical relationship there, but then we want to understand, of course, what the physical relationship is. Ocean temperature has memory just because of the thermal inertia of water. And in these ecosystems in particular, there's the phenomenon of seasonal reemergence, where surface anomalies are mixed down to depth during the winter, protected by the thermocline during the summer, and then reemerge at the surface in the subsequent winter. And so mixed layer depth is critical for driving interannual winter autocorrelation in sea surface temperature anomalies in these systems. And we know that the Aleutian low drives mixed layer depth anomalies as part of the PDO signal in these systems. That's just illustrated here by the regression of mixed layer depth on Aleutian low variability in that dashed square. And then when we looked at autocorrelation in mixed layer depth in the solid lines here at Gulf of Alaska and Bering Sea, again, plotted against Aleutian low variability, we saw a similar relationship. So it appears that the amount of interannual variability in the Aleutian low over time has an influence on whether mixed layer depth anomalies themselves are red shifted or white shifted in the system. This part of the work I'm talking about is very much an ongoing study. I'll just, before I get on to the last slide about where we're going next with this work, I'll just point out that the magnitude of change in autocorrelation in sea surface temperatures that we're observing in the Gulf and the Bering has real implications for the amount of risk for persistent marine heat waves in these systems. So we've illustrated that here in the top panels with the chance of a 2-year heat wave that's more than 2 standard deviations above the climatological mean at the highest level of autocorrelation that we've observed in the system and the lowest level. And you can see that the big spread in risk for persistent marine heat waves that we see based on the increased autocorrelation that we're seeing in these systems in recent years. And in terms of next step for this work, I'll just say that we're really interested in bringing in information about changing shortwave flux, shortwave radiative flux in the system. There's been a lot of focus on changing aerosols as a predictor both of PDO variability and accelerated warming in the North Pacific in this paper that I've highlighted here. And it seems that might be also something that's contributed to this redshifted variability in sea surface temperature in recent years. And with that, I'll thank you for your attention and be happy to take questions now, or I'm not sure if we're doing it now or at the end.
Thank you so much, Mike. We do have time for some questions. So if anyone has a question, you can put it in the chat, or you can just raise your hand or shout it out if I can't see all the hands. It looks like Jia Wang has a question.
Yes. I wonder if you remove the multi-decadal trend, which if you remove the multi or decadal variability, and then I think the residual is very small. I want because in Great Lake when we remove the multi AMO trend, and which is multi-decadal trend, and then the residual is very small. It's
Yes.
one order of magnitude smaller than the multi-decadal variability. So I wonder your high SST here is due to the natural or internal variability with the I think with the with the positive of warm phase due to PDO and also due to El Nino rather than due to man-made?
Yes. So great question. And I didn't mention that all of the calculations for autocorrelation in sea surface temperature, and also all the calculations for variability in Aleutian low forcing, all those data were detrended before we calculated the autocorrelation or variability statistics. But we did just remove the linear trend from those time series.
Nice.
So we may not have gotten at the dynamics that you're speaking to with the more complex multi-decadal variability. And that's maybe a longer conversation. But one thought is that decadal variability absent the linear trend is also the subject of interest. Whether the decadal variability is very persistently high or low at a particular time, or not. And so I think you're getting at a core question for a lot of these kinds of studies as to whether you pre-whiten data before analyzing them or remove a multi-decadal trend if that's statistically robust, or if you are also potentially removing the phenomenon that you're trying to study. So the way we came down on that was just to remove the linear trend as a known source of information.
Yeah, this is what I guess. Yeah, if you remove the linear trend, the multi-decadal trend is still there, which is internal variability of the system, of the climate system.
Yes, exactly. And that multi-decadal trend was very muted and white noise characterized in some periods, but then also very red noise shifted in other periods. So it's really that behavior of the multi-decadal variability that we're trying to address.
Mike, we have 3 questions in the chat. Hopefully we can get to them all. Katrin Eichen says, thanks, Mike, great talk. What do you think the effect of the expected super El Nino will have on this autocorrelated system or the likelihood of a heat wave?
Yeah, and that is such a great question. And there's this paper that's been sitting on my desk looking that I still haven't read from the same folks who wrote that Nature paper, looking at the 2023-2024 El Nino, which, as I understand it, did not really show impacts in Alaskan ecosystems in the way we would have understood. And that paper invokes the idea that the atmospheric bridge between the tropics and the extratropics is not behaving in the way that we're used to historically. And so that link to these high latitude systems and El Nino variability has degraded. And so that's something that I need to understand better. And then B, I think we're in this really interesting period where a lot of the teleconnections that we've understood historically aren't necessarily playing out in the same way.
Thanks.
Great. Thanks, Mike.
Yeah.
Chris Holderreed has a question in the chat. It says, on Q3 slide, is the decrease in chance of a 2-year cold period simply a reflection of long-term warming trend against your baseline?
And yes, and that is exactly right. And so we just took the linear trend for both systems, and we've got a set climatology in 1950 to 79. What are your chances of being above or below that climatology for 2 years? And that the chance of a cold spell has disappeared. Although the Eastern Bering Sea might not have gotten the memo based on the cold behavior we're seeing this year.
And the final question from Rosemary, how can communities follow what happens where next? If we have trends on the east versus west, where will additional changes be noted? Rosemary, do you want to say anything else?
Yeah, Rosemary, can you speak to that a little more?
As local community members, we're watching these changes, and we do see reactions in our community from these different weather systems that are coming in. Do we have any variables that can contribute thoughts of increasing trends on the east side versus on the west side, and how communities can absorb some of that interpretation to help communities react?
Yeah, thanks. And you're speaking about sorry, I'm not sure where you're at, but you're speaking about east side of the Bering Sea and west side of the Bering Sea?
You had information from the Atlantic and from the Bering Sea, and so I figure there's contributions in different ways when we have increasing temperatures on the east side, it affects communities differently than we do when we have increasing temperatures on the west side. But is there a way for communities to absorb some of this information and details to look for a reaction in our area?
Yeah, thanks. Okay, thanks for that context. It's a great question, and that is really one of the most difficult questions, I think, for people like myself who work in the impacts and the fisheries and subsistence and ecological impacts side of things, where people need information about this year, next year, the year after, and to make plans, and that's super challenging because of things like what we were just talking about changing relationships with things like El Nino. We're always at the end of the time series, and it's very difficult to make predictions over short time periods about consequences that people can use. One possible example, though, that I'll mention is when we're looking at that state of the Aleutian low as either a very high variability state or low variability state. One of the things we want to explore is whether the variability that's been observed, say, for the last 5 years in the Aleutian low might give us some predictive skill for the chance of an extreme temperature event over the next year or two. So that's an active area of research, but that I'll just say that remains a real challenge with studies like this. So thanks for the question.
Thank you so much, Mike. We need to move on to Cody's presentation now.
All right. Oh, get her going. Okay, and you guys can see my screen okay? Yeah, good. Okay, well, I'm Cody Szuwalski. I work at the Alaska Fisheries Science Center in Seattle. I'm a research fishery biologist. I'm also affiliate faculty at UW. And before that, I was in Santa Barbara. But at NOAA, my main duties are doing crab research, doing stock assessments for crab stocks in the Bering Sea, sitting on the crab plan team that Mike chairs, that is the first body of review of the science that's used in management at the federal level for crab in the Bering Sea. And I'm also a part of the Alaska Climate Linked Modeling Project, which is a very large group of scientists, from economists to climatologists to biologists to ecologists, that are trying to understand how we can use science to better manage the natural resources in the Bering Sea under climate change. So I'm going to talk about crab today. And in Alaska, at the federal level, we have 5 species of 10 stocks that we do management for. We've got snow crab, we have tanner crab, 2 stocks of blue king crab, 2 stocks of golden king crab, and 4 stocks of red king crab. Bristol Bay is the big one. Most of what I'm going to talk about today is focused on snow crab because it's has been one of my assessments over the last several years. And about 5 years, almost right at 5 years ago, I woke up to this in my computer. This is not something that anybody that does a stock assessment ever wants to see for the species that they do, but the collapse of snow crab was global news. I was getting phone calls from friends in foreign countries that were also paying attention to this. And when this happened, there were just questions upon questions upon questions. And today I want to talk a little bit through some of those questions and how we have tried to address them over the last 5 years. The first and biggest was, what just happened? Why did the stock collapse? Once we started to think about that a bit, we wanted to know what was going to happen next and if there was something that we could do differently to avoid collapses like this. And finally, in the last couple of years, I've been trying to understand with a group of others why this happened in the Eastern Bering Sea and not elsewhere. So I'm going to fly through these questions and related studies. Starting with the collapse. So this figure down on the bottom, the black dots, black lines, represent the survey indices of abundance of male snow crab from the bottom trawl survey that Mike's group does. In 2018, there were more crab than we had ever seen in the Bering Sea. 2019, there were markedly fewer. 2020, we didn't have a survey, and then in 2021, there were fewer crab than we had ever seen in the survey. This period from 2018 to 2019 coincided with a marine heat wave and very reduced ice, which is this darker blue line here. That's strongly correlated with the cold pool, which is the massive cold water on the seafloor that snow crab are associated with. So on the tail of this collapse, the fishery was shut down. We entered a rebuilding plan at the federal level, and we were left with lots of questions. And there were lots of hypotheses floating around as well. I think everybody had an idea of what was going on, from cannibalism to predation. I heard volcanoes at one point. So with a group of scientists, including Mike and folks up at the Kodiak lab, we pulled together as many time series to represent these hypotheses as we could. That included temperature effects, disease, discards in the fishery, cannibalism, bycatch, population density, and predation. And we tried to explain the variability in the estimates of mortality, which are this red line here, that we got out of a population dynamics model. The top are immature crab, the bottom are mature crab. These blue lines are the fits to these estimated mortalities using these covariates within the model. Across these hypotheses, temperature and density came out consistently as important in the models. And there's a variety of directions you could go in thinking about why those were important. We came down in this paper suggesting that based on these data and models, it looked like starvation played a role in the collapse. And the way we came to this was by looking at laboratory studies that looked at the caloric requirements of crab at different temperatures up here in the top left, then calculating the required calories of the population in a given year, which is down here in the bottom left. These are the two big pieces from the study, I think, that point towards starvation, because the caloric requirements jumped in 2017 to 2018 by about 4 times, and it was twice as high as it had ever been in the past. They're also, the crab were also gathered in a smaller spatial footprint than they had been historically, which you can see over here on the right. So as with any modeling exercise where I've done a regression and said this goes up when that goes up, I think there are certain caveats with those sorts of studies that make it difficult to say those with gusto. However, there were a group of intrepid scientists that pulled on that thread that you get from those sorts of regression analyses and did some actual science out in the field and in a laboratory. One of those scientists was Erin Fedewa up in Kodiak with Mike, and along with Louise Copeman down in Newport, they put together some energetic condition indices. I didn't note where this paper is published. Maybe Mike can tell us later. The upshot of this is that at sea, Erin and company would gather organs from the crab, put them in a vial, bring them back, do some measurements, and then they could get an energetic condition of crab over time. And they started this in 2019, which was right in the beginning, in the midst of the collapse, and the energetic condition of the crab was much lower than it was after, when temperatures went back to, thanks Mike, CJFAS is where this paper's at. After that, the energetic condition went back to higher levels. So we can see from this that there was a big difference in the body condition of crab during the collapse and after the collapse. But we don't specifically know that this decreased energetic condition was sufficient to induce starvation and mortality. Enter Louise Copeman down at the Newport lab. she took a bunch of crab, put them in boxes over here on the right in different temperatures of water, and then didn't give them food and waited to see when they died. It's a bit dark, but it was in the name of science, and we learned a lot from it. She was able to draw a mortality threshold on this graph that Erin had put together that shows that in 2019, the majority of the crab were beneath this mortality threshold that we had observed, that Erin had observed. So this was a great piece of the puzzle. It was an awesome research arc. The only thing that you might offer as criticism to this is that these crab were stuck in a box. They weren't avoiding predators, foraging for food, fighting with other crab for mates. This was supposed to be the coolest part of the presentation, but for some reason my video player on my government computer isn't working. Hilary Thaumann and Louise Copeman down in the Newport lab took that piece of information to heart and have put crabs on treadmills now. So this would be a video of a crab walking along on a treadmill, and they're going to measure the effects of different temperature regimes on the metabolism of crab, which is super, super cool to me. This whole thing, I think, has been one of the most interesting and instructive science research arcs that I've been a part of. We started with these time series analyses that are based on data that are collected by hundreds of scientists over decades of time. And that gave us a nice thread to pull on. And then Erin moved into field studies that gave us a little insight into the energetic condition. And then we've moved to lab studies here at the end to try and tie it all together. So it's a very, very cool research arc. It's great to be a part of all of that with a group of very cool people. I was asked to give a little bit of a population update. So it's been 5 years since the collapse. A lot has happened. This figure on the right is our survey data. So these are the numbers of crab at size over time. So the size is on the x-axis, the y-axis is time, and then the size of the polygon represents the relative numbers of crab at a given size in a given year. So you can see these cohorts of crab moving through the size ranks over time. You can see in 2018, this huge, massive crab that was bigger than anything that we'd ever seen in the past. You can see it disappear by 2021. And then we've got another big group of medium-sized crab sitting in the wings in 2025 from the survey. Tricky thing is that the fishery doesn't depend on the crab in these size ranges. It depends on the crab out here in these size ranges, bigger than about 100 millimeters carapace width. And that, the abundance of those crab has been consistently declining over time. So these black dots here are the survey observations of the commercially preferred males over time. And these last 9 years here are the lowest on record. So this isn't good news for the fishery. And this glut of medium-sized crab here might be good news for the fishery, but we have to make, those crabs have to make it to those larger sizes. And there are a couple of reasons that they might, that there are a couple of challenges to get to those larger sizes. One of them being no more marine heat waves. We've seen the effects of marine heat waves on all sizes of crab in the population through the 2018-2019 heat wave. And the other is that they actually grow to that size. Snow crab grow through a terminal molt. So when they mature, they grow one last time, and then they stop growing forever. If they stop growing at a size that is smaller than what the fishery takes, they will not contribute to fishery yield ever. I don't often get to go out on the survey, but I'm going to get to go this year again. It's great time, so hopefully I'll be able to have some more information to report back on in September. So the next question, I'm going to fly through some of this a little faster than perhaps will be comfortable for you all, but I'll do my best. The next question that we came to was, what happens next? And I spent a lot of time talking about models that were used to predict mortality for snow crab, but there are other processes that are important in population dynamics as well. You need to have some idea of what's going to come into the population, or recruitment, as we call that. We also need to know when they mature, which is particularly important for snow crab. So the most recent paper to come out of this series was one that develops models for each of these processes and then projects it forward under declining ice in the Bering Sea. Essentially, all of the climate models that we've got suggest that ice will continue to recede in the Bering Sea. And if that is the case, based on these models, the incoming crab into the population, or the recruits, will likely decline. The mortality will likely increase as temperatures increase with those declines in ice. And those two processes combined result in declines in the mature male population over time, over the next few decades. I'm not going to go into the details of what the differences between these lines are. The overall trend is that if you believe these models, and if you think the ice is going away, that the Eastern Bering Sea snow crab will likely follow the ice. So putting together models like this that you can plug in future conditions and get some prediction for what you think the stock is going to be, puts you in some tricky spots when you're trying to figure out what to do. One of the things that we talked a lot about was at the crab plan team is that if you are confident that the stock is going to collapse next year, or maybe the year after that, what do you do? Should you harvest hard to collect all of the biomass that would other die? That's kind of one end of the spectrum that you could do. Or you could just preemptively close the fishery so that the stock can have every possible chance to adapt to the new conditions and weather this storm that it's going through. Our management systems right now aren't really set up to address these sorts of questions. And one of the big reasons is something that Mike brought up, is that our models management systems are based on looking at history to try and understand what might happen in the future. And in many of these areas, we're moving into spaces that's no longer the case. I think that was one of my big takeaways from Mike's talk. That, and it's anthropogenically forced. So in spite of this, in spite of taking away that tool of being able to look at history to try and understand what you can do in the future, decisions still have to be made every day. Maybe not, and if not every day, at least every year at the federal management level. So trying to balance this this loss of the historical perspective, the uncertainty that's wrapped up in all of these models that I just talked to you about, and the need to act is really tricky, and I don't have a great path forward yet, but I think it's one of the central challenges of natural resource management under climate change. Okay, quick. So this last paper here that I talked about with all of the different models for population processes, I stuck it into a Shiny app. So if you want to pretend to be a fisheries manager for a day, you can go to this website and you can specify what you think is happening in the population, what you think will happen in the future climate, and then give the model different sorts of harvest rules or ways to determine what the catch should be, and then project it forward under different scenarios. It will spit out population trajectories, mortality trajectories, the catches that you can get. And I'm putting this up here because the question of what to do is hard, and we don't have a great answer yet. But these tools like these and models like these are one way that we can ask what if in a fisheries context. It's very hard to do experiments because it impacts people's lives. They're very large scale. So we often turn to simulation. And the hope is that we'll be able to use tools like this in concert with stakeholders, fishers, government representatives, academics, and come together and talk through different potential methods for confronting these issues in the fisheries. Okay, I'm going to speed through this really quick. The last one, this has been just the last couple of years. This has been super fun. Snow crab are not only in the Bering Sea. There are 7 other countries that also harvest snow crab. The purple dots here represent the locations they're harvested. I really wanted to know why this happened in the Bering Sea and it didn't happen elsewhere. The rest of these populations are still chugging along. So I have spent the last couple of years trying to get in touch with snow crab scientists from all of these countries to get their data and put it into a common modeling framework. Got a lot of questions like, do you guys also have mortality events? Are the relationships to environmental covariates similar to the ones that we have? And if we can get that, if we can identify common relationships, we might be able to identify generalizable conditions where we could expect a population collapse and then potentially do something about it. So the general flow of this is I get their data, I fit some population dynamics models. These are Alaska and Canadian stocks. I estimate variability in population processes like mortality. That's a big one that I'm interested in. And then I try to explain the variability and mortality with demographics and environment. I just want to point out here that for the stocks that I have in this so far, which are just Canadian and Alaskan stocks, there is a positive relationship between temperature and mortality. So the hotter it is, the more mortality you see. But in spite of this shared relationship, the Canadian stocks have not collapsed. And I think that perhaps the reason for this is that our currents are working in opposite directions. And that influences the temperatures experienced by the snow crab on either side of North America. So these top temperatures are the temperatures occupied by Alaskan immature and mature snow crab. And then these temperatures down here are those experienced by the Canadian populations. So this is still in early days, but it's been a really cool opportunity to talk to other scientists around the world to try and learn from them, see how they're approaching management, and talk about common problems that we all have. Since I'm at 2 minutes, I'm going to skip over that to say thank you to a large suite of co-authors, Mike being one of him, and many others in his lab, and take, I guess, maybe one question given the time that I've got left. Thanks for listening.
Thank you so much, Cody. This was a great presentation. Questions? I know I have one. So Cody, reading your papers and seeing your talk, it strikes me that it would be really great to be able to predict this collapse, right? I mean, 2018, it was looking great. Snow crab were super abundant, and then this crash. What do you think needs to happen? What tools do you need for NOAA to be able to predict such a collapse? What's missing? I saw you mentioned ice. I think that makes a lot of sense, but how could we be able to predict if you could have anything you wanted?
Oof. So my first reaction to the question, I thought about this a lot. If I could have predicted the collapse, what would we have done differently? And that's a hard question just in and of itself. I don't know what, I don't know where to go with that, because you can either say, hey, we should go harvest all of these crab, or we should leave them all out there. So maybe we'll come back to that. I think the most important thing from my perspective is continued survey data collection. The survey that we have is amazing. There are not many other crab populations in the world that have this history of data that we have. And that is really, really essential for being able to do these sorts of analyses. And it's also tricky because we're in funding environments where the surveys are uncertain going forward. So I think surveys are the critical thing that we need to keep our finger on, and not just in the areas that we've got. We've been doing the northern Bering Sea for a while. That's a potential climate refuge for snow crab because the ice will recede to the north and they'll likely follow it. But we just started that in 2010, and it's because there aren't a lot of fisheries up there. Sometimes the impetus to continue that is trickier. But I guess establishing surveys in the northern Bering Sea and beyond, and continuing them would be the thing that I would want to have going forward to understand the dynamics of snow crab.
Okay, thank you. We have a question. So I know it's 11, you guys. If you need to leave, we understand. Cody, and Mike, do you have just a couple minutes? We've got one more question in the chat that I see. Rosemary says, we are seeing changes in distribution of salmon. Is the crab distribution changing as well?
Yeah, absolutely. The fishery for snow crab has occurred farther north in the last 5 to 7 or 8 years than it really ever has. The larger crab are farther north. Historically, you could get them down south of St. Paul and St. Matt's. Well, definitely down from St. Matt's, but over time they have gradually shifted north. One of the interesting things with the collapse is that tanner crab, which is another very similar crab to snow crab, but has usually been the farther south, it has pushed out west and farther north than we've ever seen it. So we've seen in this last, after the heat wave, there was an explosion of the tanner crab population, and it's kind of backfilled in some spots for the snow crab population.
Thank you. I see your hand raised, Indu.
Yeah, Cody, great talk, and Mike too. So I am not a fishery biologist. I'm a microbiologist, but I studied deep sea Atlantic crab briefly from the microbiology perspective. And one of the things I learned about them is that they are segregated by depth. So the juvenile crabs usually migrate to the deeper water to escape the cannibalism or predation and whatnot. Do these snow crabs have the similar pattern, or like how does that
Yeah,
work?
they do. They absolutely do. It's a great strategy if your parents are going to eat you to try and run away from them. So it's common among crab. For snow crab, it's actually opposite in terms of depth. They settle into more shallow grounds in the northern part of the Bering Sea, and then over time they move into deeper waters as they mature. And then we also think that there's a kind of a back and forth of the biggest crab during mating season.
Okay.
So there is that. And one of the other things that often came up with the collapse was whether or not the crab went into deeper water. So back to the first question about what I would love to have, it's expanded survey coverage everywhere. If we could see more into the depths, that would be great. So
because with the rising temperature or heat wave, the juvenile will have little chance to survive, considering the microbial pathogens that can impact, and then predation as well.
Yeah, absolutely. For snow crab, the juveniles, it's kind of interesting. They're the reason. I was going to see the reason they're called snow crab, but I don't actually know the exact reason they're called snow crab. We do know that they are associated with the cold pool. They like really cold water, and one of the reasons that we think that they really like cold water is that it keeps predators out to some extent. So the disappearance of that cold water will likely have consequences for the juvenile crab for sure.
Super cool. Thank you.
Yeah, thank you.
Thank you. Any further questions? We have time for maybe one more question for Cody or Mike. Okay. Seeing none, I guess we'll say thank you again to Mike and Cody. Thank you everyone for coming to this webinar. We appreciate your presence here today. And we'll see you next time.
All right. Thanks,
Bye.
everybody.
Thank
Thank you
Thank you.
all.
Bye.
Yeah.